to do is look for other ways. So we can look for experimental evidence. So one of the things that we talked about last week was looking at how many products were formed or what products were formed. That can help us determine what type of mechanism. The other thing we can go through and do is look at our rate law. So we can look at kinetics. How fast does the reaction occur? Okay. So in each of our mechanisms that we outlined, they varied on different rate limiting steps. And in those rate limiting steps, they had different things in them, which means our rate should change, right? Or our rate law should change for each of these. So to go through and do that, you'd go back to 152, you get this big old fun table looking at rates and concentrations and evaluating how they change and all that fun stuff. Okay, so within those first two experiments, you should notice that the only thing that changed was we doubled the OH. What happened to the rate? It also doubled. So what does that mean? Our rate is directly proportional to the concentration of OH minus, which, as you guys were all jumping to, is referred to as first order. What happens if we take a look at the next sequence of reactions? We double our concentration of our substrate. What happens to the rate? Also doubles. So our rate is proportional to, I'm just going to write sub or substrate. Okay? So we now have that rough relationship. This you go through all your 152 stuff, and you end up coming back to figuring out what your overall rate law would be. We'd say rate equals your rate constant times the concentration of substrate times the concentration of OH minus, okay, or NaOH. Why did I ignore the Na in OH minus? The Na is just a spectator ion. It's a sodium. We don't really care about it. Okay? It's not going to have any real effect on our reaction. So we now have a rate law for our experiment. We can then push this to what type of mechanism happens. So the first thing we could do is say, well, what changed as we went through this reaction? What type of reaction was it? It's a substitution. When we think of substitution reactions, are there multiple types of mechanisms? Yeah, we've got two types, SN1 and SN2. The 1 stood for unimolecular. Okay. So I'm seeing a couple people hold up 2 fingers. That's fine. What you're remembering is 2 steps. Okay, so you're associating the mechanism, and I personally had a hard time with that because it's SN1 with 2 steps, and I have a big issue with matching those numbers up. Okay, the 1 is coming from it being a unimolecular reaction. To figure out if it's a unimolecular or some other molecularity, we have to look at the rate law. So we look at our rate law. We say, well, what things are in the rate law? Well, I've got 2 things in my rate law, which means this is not unimolecular, this is bimolecular, which means we're running under our SN2, our second type of substitution mechanism. Okay? So once we have that rate law, we can start to evaluate all sorts of fun things. So what happens to our rate if the OH minus is doubled? It should double the reaction, because all we're doing is keeping everything else. Where's my eraser? There it goes. Okay. All that happens is we're taking our rate, substrate stays the same, but now I'm doing twice the amount of OH minus. What happens? I get double the rate. Okay. So on a test, more than likely what you're going to be given is just a reaction and say, what happens if we double the concentration of this species? Okay. So you have to recognize by looking at just the reaction, which is partly chapter 9, what type of reaction it is first off, then what type of mechanism. If you know the mechanism, you now know the rate, you can now answer the question. Okay? So the one where we just double OH minus is relatively straightforward. Okay? So that question is fairly common. It does pop up fairly often, but it's not really all that challenging. If you know the rate law, you're good with it. Okay? The one that gets a little bit trickier is the one we've got in blue. What happens if the solvent, okay, and ultimately solvent concentration, is cut in half? When you look at the rate law, is OH minus the solvent? No. Is substrate the solvent? No. Well, solvent doesn't show up in my rate law, so what should happen to the rate? Absolutely nothing. But what happens to the rate? It quadruples. What? It doesn't show up in our rate expression. Why is it quadrupling? It comes back to the definition of what those brackets mean. Those brackets mean concentration, which is the moles per liter of solvent. So if you cut your solvent concentration in half, that's going to double all of your reactant concentrations, which gets us the quadrupling of the rate. Fascinating little question. Okay. While kinetics are important for looking at our reactions, we can kind of sideline it for the most part. Okay, so you will see some questions on it on your test, maybe one or two, and then on the final you might see just one question on it. Okay? So the direct rate law stuff is really something we can kind of relegate to 152, and we just assume, because that's always a good thing to do, that you know it, know how to manipulate it, and we don't kind of stress about it again. Okay? So this is the supporting for the fact that we do have these two types of mechanisms. Our biggest aspect that we want out of this is not this evidence for the two mechanisms, but can you use the two mechanisms? And then once you know what the mechanism is, what things are going to control whether that mechanism works or not. Okay? Yes?
What are the differences besides obviously increasing the rate by having something other than a first order reaction if it's like if one of them's squared, for example?
So I'm going to dodge that question, okay, real fast. I guess I had too much fun this weekend. We don't have to worry about that because we don't see that in our reactions for organic. Okay, so we don't have to stress about it. We're looking at first and second order reactions, and our second order reactions are always mixing two different species.
Is there a place it would show up?
Is there a place what?
It would show up besides organic?
In this, yeah. Besides organic, anything outside of organic, any kind of chemistry, yeah. Any inorganic reactions, think back to 152, you saw those reactions pop up a lot. Okay. So, now that we know we have these two mechanisms, let's look at them again in more detail. Okay. So, in theory, these reactions match up. So, when we're looking at our SN1 reaction, we're tying two things. Okay, we're breaking a leaving group bond, and then we're forming a new bond, okay, our bond to our nucleophile. And yeah, it didn't quite tightly perfectly. So when we're saying we're breaking CI, that I in this case happens to be our LG bond. Okay, and when we're saying we're breaking CL, that happens to be CCl, that happens to be that is our carbon nucleophile bond. Okay, so if we look at our overall reaction, you'll notice there's an extra step in this because that is possibly something that could show up. Okay, you may occasionally see this acid-base step jumping in there as well. Okay, and we will talk about that. That's the tail end of chapter 8. So we've got what's happening in our primary system. So in that very first step, what I've got labeled as mechanistic step 1, what type of mechanistic reaction was that, according to our rules from chapter 7? That was what? Heterolysis. All we're doing is breaking a bond. Okay, that is naturally or necessarily going to form this carbocation. Okay, and I cannot stress enough how important it is that we have a carbocation. Everything that comes out of understanding the SN1 mechanism, or what things control it, centers on carbocation. Okay? We'll address that why in a second. The next step of this was what? What happened? We have a coordination. And we've now officially done our substitution. If our substitution product at that stage happens to be charged, charge is bad, we'll go through a secondary reaction. That secondary reaction is almost always an acid-base reaction, okay, to get us to our final state where we just have our nucleophile on there and we've done our official, full, safe substitution. Okay. So let's ignore that last step for the moment and just look at our heterolysis and our coordination. Which of those two steps is going to be the hardest step to do? The heterolysis tends to be the hardest step of the SN1 mechanism. Okay? You are breaking a polar bond to form a carbocation. Okay? Carbocations are charged, high in energy, not a good thing to be. So we're looking at a very endothermic reaction there. Not easy to do. Okay, so when we're concerned about the SN1 mechanism, everything we're going to be looking at is how do we make that step faster? Because if that step goes faster, I can then do the rest of my steps. Okay? If that step is incredibly slow, no reaction can ever happen, regardless of what happens, would theoretically happen after that step. Okay? So, we're all concerned just in that rate determining step here, or rate limiting step. So what would our rate law be for this then? For this reaction? Rate equals K. There's your first easy answer. Now it gets harder.
The substrate.
The concentration of just the substrate. Why just the substrate? If you look at that step, there's only one reactant, and it is just the substrate. So our rate determining, or our rate law is now just going to be the concentration of the substrate. Okay? So I can change the concentration of the nucleophile, has no effect on the reaction. I can make the nucleophile a wicked, awesome, fantastic nucleophile. Okay, what would make it a wicked, awesome, fantastic nucleophile? Okay. Electron rich. Okay. Why does it need to be electron rich? What's the definition of a nucleophile? It donates electron. So if I've got a good nucleophile, it better have a lot of electrons. Okay, some other terms that got floated out there, a weak base. Okay, is that necessarily going to be true? No, our weak base donates electrons to hydrogen. If we have a good nucleophile, it very often is also a good base. Okay, not always. There are conditions behind that, but they tend to match each other, so we got to watch out for those. So we're looking for something that is wicked, wicked negative. Okay? If I make something super negative for my nucleophile, it's not going to affect the SN1 mechanism at all, because it's not in that first step. I don't need to worry about it. Okay? So that gives me some information about the nucleophile. It's irrelevant. I don't care. As long as it's present, the reaction goes. Okay? What other things could potentially contribute to whether this reaction would go or not? Why the stability of the carbocation? It's going to be more likely to happen because if I drop the energy of that, it's now going to be an easier jump to get over to make it. So if I'm looking at the SN1 mechanism, one of my primary concerns is the stability of that carbocation. If it is stable, this reaction works phenomenally well. Okay? So in Chapter 9, you're now going to address each of these pieces. The leaving group, the substrate, the nucleophile, and the solvent. Okay? I keep it at 4 things. Your textbook brings in a 5th, and I'm still trying to figure out why they're bringing in the 5th. It doesn't make any sense to me. Okay? But there's 4 things you need to be constantly evaluating and ranking as you go through and look at these mechanisms, or deciding on a reaction. Okay? So it's kind of a neat little summary. We've got our rate law and our lower left. Okay? K times our substrate. Our 4 things: substrate, leaving group, nucleophile, and solvent. Those are the 4 primary things you need to be worried about, which you'll notice are also the 4 things that are nicely colored in my little drawing. Okay, you may not see that, but that part is in blue. We've got our substrate. In purple, we've got our leaving group, which I'm going to leave you to interpret. Red is our nucleophile, and green is the solvent. Okay? So you need to know and recognize those pieces. You'll notice that green is difficult to see on the board. There's a reason I relegated the solvent to being the color green. Because how important is it to look at the solvent? Relatively minor effects. Okay? So that's why it's virtually impossible to see it on the screen. Okay? What happens if we look at the SN2 reaction? Okay. Same things happen as the SN1, except now instead of breaking those into smaller steps, we jam it in all in one instantaneous step. Okay. You may see this kind of image show up here. Okay. And some people kind of misinterpret what this means. What is this kind of intermediate thing? And using the term intermediate was a bad term to use. What is that?
It's the transition state.
Or if you're a poor speller, okay, you read the transition state. It's our transition state. The transition state does not exist. Okay, it is not an intermediate. But what we are trying to show with the transition state is that our nucleophile is coming in from the backside of the leaving group leaving. So as the nucleophile comes in, the leaving group can then push out. And we end up passing through this trigonal bipyramidal intermediate. Okay, if you think all the way back to your Gen Chem geometry stuff. Okay. Officially, that structure can exist. Why can that structure not exist?
Can't be there at the same time.
We'd have too many bonds to our carbon. It's exceeding the octet. So all we're trying to show is that we're transitioning from being a reactant to becoming a product. The transition state is what's happening at that peak. Okay. A hair on this side, which bond is shorter? If we're closer to the reactant side, which bond is shorter? Let's call it bond 1 or bond 2. Okay. Are we closer to the reactant or closer to the product with where I've got my arrow? Closer to the reactant. What's bound to the reactant? The leaving group. So which bond should be shorter? The leaving group bond should be shorter. It's now a little bit closer to the nucleus. If we now shift just to the other side of that, now which bond is shorter? The nucleophile, because I'm now on the side of it becoming the product. That is now going to be a closer or stronger bond. So it is a very dynamic situation. As one comes in, one leaves. It's not this nice stepwise process. Okay. If we looked at the rate for this reaction, what would our rate be? Well, here's your first step. Rate equals K.
Substrate concentration.
Now we're looking at our substrate and the concentration of the nucleophile. We need them both in there because both are involved in that rate limiting step. We have arrows from both of those. Okay? So if we think back to what we said with the SN1, I said that the SN1 I could make a wicked, stupidly strong nucleophile, and it has absolutely no effect on the reaction. What happens if I do that same thing with the SN2?
Speed up the reaction.
It's going to speed up the reaction. Because the nucleophile is now very important to this reaction going. If I don't have a nucleophile, the effective concentration in my rate law is 0. Well, your rate is going to be 0. But if I can make that nucleophile more reactive, we're effectively increasing its concentration, and our rate will speed up. Okay? So having an understanding of the rate laws and the mechanisms can help you predict certain aspects that are going to be important when you move into Chapter 9. Okay. The other big term that comes out of the SN2, backside attack. Why? Where does the nucleophile attack from? The backside of our leaving group bond. Okay, so the backside attack is a really important aspect to remember. The other big term that comes out of this is something known as steric hindrance. Steric hindrance is a fancy way of saying electron repulsion. We just have large groups of electrons getting near each other, and they hinder and repel away from each other. That's what's happening when we're talking about steric hindrance. So those are going to be our important concepts for the SN2. And I just lost connection. Hopefully it stays. Okay. So repercussions of the different mechanisms. What are the possible results for the following reactions? Okay. So both of these reactions starting with the same material, do we expect the same product? Okay. Why would we not expect the same product? It's the same starting material and the same reaction. It's a substitution reaction.
But there's an intermediate in the SN1.
There's an intermediate in the SN1. Does that necessarily change the product? Don't I still get the nucleophile going to the exact same location? Yeah, I do. Kind of.
The hydrogen bonds to the chlorine, right? Or the chlorine takes on this acid base.
There is no acid-base reaction in this case. We don't need that acid-base step.
In the SN1, the nucleophile or the iodide can attack from either the top or the bottom.
Why does it matter if it attacks from the top or the bottom? So that is absolutely fair. When we form a carbocation, we have a p orbital, okay, an empty p orbital. That's why it's a positive charge. Electrons can either come in from the top of that p orbital, in which case our bond is forming above our carbon, or the electrons from our nucleophile can come in below, in which case our bond is forming below the carbon. But why do I care?
Because it's going to change
It's gonna change, it's gonna be a completely different product.
There is no real resonance in this one, and we can address that as another issue. This is going to come back to what is special about that red carbon. It is a chiral carbon. So that fun chapter that you're like, oh my God, I can't understand anything, and seeing all those stupid visualization, that's awful, I never want to see that again. Slap in the face. Here it is. Okay. This is our primary difference between our SN1 and our SN2 reaction. If there's a chiral atom, under SN1 reactions, we lose chirality with our intermediate because we now have that carbocation. And with that carbocation, we can have the nucleophile either form a bond above or below, which results in two products. When we move to the SN2 happens all at the same time. So that iodide must come in from the back side of that carbon-chlorine bond. As it comes in from the back side, that is necessarily going to result that our carbon-iodide bond is now in the opposite direction of our carbon-chloride bond. Okay? And there is no other option. So under the SN1 conditions, I get two products coming out of this. Under the SN2, I only get one. Okay? And there's some interesting results that come out of this. In the SN1, what is the relationship between those products? They are enantiomers, assuming there's only one chiral atom. Why making that assumption? What happens if I threw in another chiral atom? Said make this an OH. Whoops. Make that a wedge OH. Does that change through the course of the reaction? It doesn't change through the reaction, so that one stays that wedge, but the iodine can still come in backwards and forwards. So at the position of where the chemistry occurred, that would indeed be mirror images, non-superimposable mirror images. But if there's another chiral atom present, that one never changes because no chemistry happened there, which means now your relationship would be diastereomers, not enantiomers. Okay? Fun question that comes out of this. Actually, not quite that fun question yet. Let's take a look at the SN2. Okay? We end up with just one product, so we don't have to worry about, oh, thank God, we don't have to worry about chirality anymore. Thank goodness. There's only one product. Not quite. I mean, it is still one product, but what do we have to worry about?
Which product it actually is?
Which one of those two did I get? Okay. If we start S, our iodine comes in from the backside, which now puts our highest priority group the complete opposite direction of where it was. Nothing else changes, which means we end up with the R form of our product. We get an inversion in our stereochemistry. Okay. Next fun question. Optical activity. You run the SN1 reaction. Are your products optically active? No. Why not? They cancel each other out, so our optical activity comes out to nil. When we run the SN2, yes, we get optical activity. It ends up being the opposite of where it's, let's avoid that. Okay. We maintain that optical activity. Okay. So these are kind of the tricky aspects that comes out of these. Okay. So how many of you can actually see this and visualize this and are okay and like, yeah, I got it. I understand how those things are changing. Okay. 2 or 3 of you, okay. For the rest of you, let's take a look at our visualization. So in the very first step of our reaction, I don't know why there's a red dot there. Oh, I do know why there's a red dot. Ignore the red dot. If you don't see the red dot, then don't worry about it. In the SN1 mechanism, we form that carbocation. What's the hybridization of that carbon?
Or sp2.
It is sp2. Being sp2, can it be a chiral atom?
No.
No, because it has to have 4 different things attached. So in our very first step of our SN1 mechanism, chirality gone. Okay? So now we want to go back to all of our lovely orbital diagrams. Okay? What would this structure look like with the p orbital? Where is that p orbital? Okay, it's kind of fun seeing people like playing a trombone. Okay. Trombone, the instrument. Okay, never mind. Your p orbital is coming in and out of the plane. Okay. Virtually impossible to draw that. So what would happen if we now took the plane of our paper and we just kind of rotated that up? Where would the p orbital now be? Up and down. So let's go through and draw that. Okay. If we went through and attempted to draw that, I'm going to write ET. What does ET stand for? Don't tell me extraterrestrial. ET stands for? No, as a hint, this one's ME, and this one's PH. Phenyl, methyl, and ethyl. Okay, so we're looking at the substituents attached to that carbocation, so we can make some abbreviations with that. If we do that, the phenyl is now pulled out of the plane at you, so a nice big wedge. What happened to the methyl? Dashed going away from you, and then our ethyl's in the plane. So our p orbital we could now draw nice and sort of neatly up and down. So why is this a problem when we look at the SN1? Well, our nucleophile now comes along with its electrons, and it says, oh, there's an empty place to dump electrons. Or, oh, there's an empty place to dump electrons. The result is that nucleophile is either going above or below the plane of our structure, which now gives us different stereochemistry out of the products. Should I draw those products? Sure, okay, we'll accept it. So we'll have to color code here. For our red one, nuke, phenyl, oof, that's a methyl. Our purple one will be our nucleophile, our ethyl, phenyl, and methyl. Okay. So we end up with these two products. What is the relationship between those two products? They are enantiomers. Where's the mirror image? Where's that mirror dropped? Okay. We put a mirror there. They reflect perfectly across it. Stereochemistry. Let's assume the nucleophile is highest priority. 1, 2, 3, 4. We would now be turning clockwise. Thank you for the help. I am serious if someone thought I was kidding. 1, 2, 3. I have a hard time with clockwise and counterclockwise. Even withdrawing the structures a million times, I still get R and S backwards. We now go through 1, 2, 3, and we have counterclockwise S. There's our enantiomers. Okay. So this is a natural kind of repercussion or result of following this mechanism. So if we understand what changed and how it changed, and we come up with a prediction for our mechanism, the rules and things that we have to memorize are buried in it. Okay? It's not an extra thing to memorize that I'm producing two products. It's a natural repercussion of understanding how the electrons move and what those individual results come out as. Okay. How many think that's easy to see? Really? Okay, cool. That actually kind of makes me feel somewhat good. Okay. Got 2 or 3 people. It's not easy to see. Okay? It takes practice. Okay. The next part of this is you may leave this class thinking, oh, I think I understand it now. You don't understand anything until you go through and you do it on your own. Right? So please do not walk out of here saying, I don't need to practice this until the exam, because that will not work. You need to practice this and struggle through it. Okay? So we could look at the nicer images of this. Your textbook kind of put this together. Where's the p orbital now? If I drew the p orbital in, let's draw it into this top structure. Where's the p orbital? Kind of in the plane of the screen. We'd have one p orbital over there, dash, dash, dash. One lobe of the p orbital on the other side. Okay. Same ultimate idea. I think it's easier to see top versus bottom as opposed to something aimed at me. Okay? So, 2 products out of your SN1. Questions? Okay. SN2. Okay. There is no intermediate. So when we're drawing out our SN2 mechanism, we have to address where that nucleophile attacks. Okay. Where does it attack? It's going to be a backside attack. In our arrows, you'll typically see I'm always trying to show it as best I can from the backside. But officially, where's the backside in this case? Dashed away from us. So if you want to get really weird on this, make your arrow look like a fishbone. Okay. Coming in from the backside of that bond. And then our chlorine is then leaving out the front. Why does it have to come in from the backside? The chlorine's got a lot of electron density. That electron density will prevent the nucleophile from coming in from the top, okay, or coming in anywhere near where the chloride is leaving. You have to do that backside attack. Okay. This is another one that's kind of difficult to visualize, because if I drew this out, okay, we would probably get something looking like this. Whoops. Yeah, it looks a little weird. Okay. Okay. What's going on with that? What would I complain about? You're not showing the appropriate bond angles. You got things cramped up on one spot. Okay. What ended up happening? Okay. As that nucleophile came in, it had to force the other groups up the other direction. Okay. What we're looking at is effectively an umbrella being caught by the wind. Okay. Our nucleophile is coming in from underneath the umbrella, which now is necessarily going to push all of the other pieces up the other direction away from it. Okay. That is where we're getting our inversion from. Does it have to be inversion? This is kind of a tricky question. Okay. We'll always get inversion, but do we get inversion of stereochemistry? Not necessarily. Okay. Your nucleophile could be a lower priority. If it's lower priority than some other group in there, you may not see an inversion of stereochemistry. You still get an inversion of the structure, but you don't necessarily switch from R to S. Okay, or from S to R. Okay. Isn't a whole lot else for me to show, unfortunately, with that one, short of potentially trying to do it with my hands. Is that worthwhile? The people that are making faces with me saw me do it with a model kit, so that's not really fair. Okay. So, tetrahedral structure. Wrist is one atom. Each of my fingertips is another atom. Okay. My wrist is the leaving group. Where does my nucleophile have to attack? Has to come in from the bottom. What are these things? Groups of electrons. What happens as my nucleophile gets in? They repel. And ultimately they should snap the other direction, but they're not going to do that. Okay. That's why we're getting that inversion. What happens if those groups of electrons are really, really big?
It's harder.
And your nucleophile never makes it. Okay. So it's evaluating the geometries and the structures of each of those types of things to say, what's the natural repercussion that's going to fall out of this? Okay. Questions on substitution before we move into elimination? And it looks like I didn't stepwise the elimination. I apologize. Oh. No questions on substitution?
Quick question, would this even take place? It seems like that iodine would be able negativity better than chlorine, so it seems like you wouldn't.
There's a couple things at play with that. The first thing at play is that you're ranking iodine as a nucleophile versus chloride. We haven't talked about nucleophilic characteristics. Iodine's actually pretty good. Okay. There's a larger issue, sort of, no pun intended. What's on the backside of that chlorine leaving group? So the analogy that we could do, which would be a little weird during class, we won't do that, okay, is we could come up here and someone can grab each of my fingertips and act as atoms. Okay? They're acting as atoms with larger electron density than my fingertips, which means what happens is the nucleophile tries to get up. It's got to dance around all the hands. We've got a very sterically hindered structure here. Okay? Would this mechanism be very likely to occur under SN2? Probably not, because of all those big bulky groups preventing the nucleophile from attacking. But again, in chapter 8, we aren't asked to predict whether the mechanism exists or not. What we're saying is it does. Do it. What are the natural results that come out of it? Okay. So a good way to read ahead. Awesome, Gio. Other questions? Okay. When we move to the elimination, okay, we're going to again run into two options. Man, this figure sucks. When we look at the E1 elimination, what we run into in this case is that we don't have a stereocenter. So we don't have to worry about chirality per se. But we do have the possibility for cis-trans isomers. So given the proper starting material, we can either end up with a cis product or a trans product. Okay. All of that is going to be based on understanding what happens with how the mechanism works. So in our very first step for the E1 elimination, we lose the leaving group, forming a carbocation. Okay. At that point, around that carbon, what type of bonds, do we have? We'll try and draw them in. So there's our carbocation. What types of bonds are around the carbocation? So we could go through and call it secondary. I'm not even asking that. What are the bonds? What types of bonds are around that carbocation? I heard some single, but more importantly, I wanted sigma. What was our issue with sigma bonds from chapter 3? They can freely rotate. Okay. So because that is still a sigma bond, I can rotate about that, which then does what? Well, that's going to change the orientation of these two groups relative to this group. Well, if those orientations change, is that going to change my product? Yes. Why? Because when I go through to form the final product, what type of bond do I have through the middle of my structure? A pi bond. And as we learned in chapter 3, what's the issue with pi bonds? They don't freely rotate. Okay? So your textbook went through and tried to provide this image. I think I've got my version of it, which I think looks a little bit nicer. Okay? Where we've got our base coming in to remove the hydrogen to form our pi bond. Okay? But what ended up happening is we did various rotations about the sigma bond to change the overall orientation of our hydrogen relative to the carbocation. By changing that orientation, we change where the phenyl groups are relative to each other, and we now have the potential for forming both products. Which product should be formed in favor? So the bottom structure is that guy, or close enough, and the top structure is, okay, so we got trans up top, and we have cis down below. Which product should be favored? Why the trans?
Because the phenols are so huge.
The phenyl groups have a lot of electron density, so what happens when we look at that carbocation? We're going to rotate that sigma bond to get those phenyl groups as far away from each other as possible. Once we're at that lowest energy, you're going to love this, Newman projection, now the elimination can occur, and we're now locked in that permanent position. So when we're looking at the E1, trans is our primary product. Cis is possible, just not quite as likely. Okay? And it really depends on how much sterics are involved. If we have relatively small groups around where our double bond is forming, we're going to end up with equal amounts of cis and trans. Because if they're small groups, they aren't really contributing to a difference in energy, which means we get both products. If they are massive groups, we see a much larger favoring for the trans because those massive groups want to get away from each other. All right, and let's see if this is indeed the system I thought it was. Good. So we've got my version of it. Okay, and again, I know there's a lot on it, but what we're doing is getting to our intermediate again with our carbocation. But now what I went through and did was aligned it so that we can see the carbocation perfectly up and down in the plane. Okay? Which then necessarily means that our other groups around our carbocation are either going to be wedged or dashed. Everybody okay with that orientation? Kind of get the idea of it. We took our trigonal planar structure, we rotated it out so we can see the p orbitals. So our p orbital is now up and down in the plane of our paper. To do the elimination, the hydrogen has to be in that same plane. Why? What is the hydrogen contributing? Electrons. What are we trying to make? A pi bond, which means I need p orbitals to overlap with each other. Well, one of those p orbitals that we see up there is that carbocation with no electrons. The hydrogen has to supply all of those electrons. Can it supply the electrons to making a pi bond? So there's our p orbital. If our hydrogen is aimed over here, are we going to get pi orbital overlap?
No.
No. Where does the hydrogen have to be located? In the exact same plane as our p orbital. As long as it is in the same plane, we can now get that p orbital overlap. Okay? So, we've got two possible systems that can come out of this. To the left, I did no further rotation. We just left it alone as drawn, and we went through and did the elimination. So what ends up happening, we take the electrons from the bond, dump them into the pi system. We would officially just have H plus floating off on its own. I still haven't been convinced enough that we need to show a base, pick that up, but you will have to do that in your homework. Okay, so we would have a base actually show up here. Share electrons with the hydrogen. Okay, and we would then have our bond between our base and our H. Whoops. What's the necessary result? Well, all I've done was just maintain the hydrogen in that plane and then just said, what happens? Well, nothing else changed, so I maintain the orientation. The methyl will still be wedged coming at you. The other phenyl will still be dashed going away from you. We look at the other carbon. Where's the phenyl? Coming at you with the wedge. Didn't change anything. That's a really weird way to look at a double bond. You got wedges and dashes in it. It makes no sense because they're all planar. So what do we do with that structure? What we're looking at is this structure right now. What do we do with it? It's a better way to look at my iPad. All we did was turn it flat. Please don't break anything. Okay. That is now our relationship. What is the relationship between our largest groups? They are trans away from each other. What happens in the cis situation? What did we do? So we're now looking at this side of our map. That is jumping all the way to the product. Before we get to the product, I want you to first evaluate what happens to go between, let's call it step 1, or product 1 to product 2. I rotate this hydrogen down and around so it is now aimed straight down. Okay. What necessarily happens? So if we take that hydrogen, I'm going to have to face with you. Take that hydrogen, I'm going to pull it towards me, all the way down. That methyl was coming at you. What happens when I pull that hydrogen down? Now it'll be going away from you, the other direction. What happens to the phenyl that's aimed away from you? Well, if I pull that hydrogen, it's now going to be coming at you. Okay, Okay, so it's not just a question of now, oh, let's just change pieces around so we align it. We have to make sure that we maintain the exact same alignment, the exact same spatial arrangement of those groups to get to the structure. Now that the hydrogen is in, again, the same plane as our p orbital, but now it's aimed down, what happens? We go through and again do our elimination, and now our phenyl groups are on the same side. We have the cis product. Okay. One last real quick. So if we take our p orbital, that's where we started, nice normal p orbital. Right? Here's our hydrogen. I'm going to say the hydrogen atom itself is the green cap. In our trans arrangement, this is what we did. We said that had to be our perfect alignment to allow the elimination to occur. Right. What happened to get it to the cis? Are they still parallel? Yes. As long as they are still in that parallel alignment, we can do the elimination. But they can be parallel up, it can be parallel down just as easily. Okay, questions?
Which of the ones being rotated again? There's which ones being rotated because we're kind of confused.
Which bond needs to be, or which side needs to be rotated on the purple side? Okay, so what I went through and did, let's see if I can clean some of this up a little bit. Sort of erase all of that. Okay, so if we take a look at this alignment, what we've done is taken this hydrogen and we grabbed it and I pulled it forward at you and around so that it's aimed down. Okay, I'm rotating on this side of the molecule. I did not touch the alignment on the other side of the molecule. You'll notice that the phenyl is still aimed at you with a wedge. The hydrogen is still aimed away from you. Okay. Could I have rotated the other side? Yeah, absolutely. That would absolutely still be a fair way to do it. Hopefully this connects. Okay. But for me, for some reason, it was easier to do the other side. All right, you'll still end up with the exact same system of products. Other questions? Don't look too depressed. It only gets worse from here. You should be happy now. You can be sad on the last day. Okay. Since we're talking about stability, because we said the trans was favored over the cis, okay? If we go through and take a look at this reaction, I tell you, E1 reaction. Okay? To perform this elimination, we need to remove that hydrogen from a neighboring carbon. So in this case, I removed a hydrogen from over here. Okay? And there were two possible ways that I could have done that, where I ended up with the cis product or the trans product. Yes? Everybody agree with that? Okay. What makes this question a little bit more challenging? What do you mean, which one am I going to get?
If you're going to end up with a trans and cis orientation.
So deciding which alignment we're going to get, trans or cis, is going to come from looking at the actual stereochemistry, the wedges, the dashes, on all of those atoms, and looking at that major alignment. Okay. Our shortcut for the case of the E1 is going to be which product is favored.
Don't you have a cis and trans?
You're right. Let me fix that. Which product is favored when we do the elimination? Trans. So which product should we get? Trans. Okay. We're looking at relatively small groups, so we're probably saying maybe a 60-40 favoring of the trans. Okay. Did I have to pull those red hydrogens off?
No, you do.
So when we do the elimination, it's removing a hydrogen from a neighboring carbon, okay, or the beta position. So if we look at that carbocation, there's our alpha. Where's beta? Oh, there's beta. Is there another beta? What does that mean? There's another product. Okay? That is also a valid product. This is officially chapter 9. How do we decide between all three of those products? Okay, well, we came up with one option, trans. okay, because trans was lower in energy than our cis, so we'd lean towards the trans. But what about this guy? What's going on with that? Okay. That's a little weird. How is that happening? Why is that happening? Trying to predict that is a little bit more difficult to come up with. Okay. It's still going to come back to stability. Okay. Which of those double bonds will we predict to be more reactive? It's a very hand-wavy argument, but it kind of works. Why would the bottom one be more reactive? Interesting call on that. We've got a larger dipole by having that double bond on the end of the structure. The analysis that I like to go through, what makes each of those reactive structures? Electrons where? No, won't quite accept ends. In the pi bonds. So if I'm going to look at an alkene reacting, what do I need to find? Take my pi electrons, and what do those pi electrons need to do? They need to donate where? Outside the structure. Running a reaction, those electrons need to leave the structure. What happens when the electrons try and leave that direction? There's a CH3. So I'm comparing carbon to hydrogen. What's the difference between carbon and hydrogen? Size. Carbon has more electrons. What happens when electrons get near electrons? They repel. That method doesn't work as an escape route. What happens out that way? Same thing, no escape route. Hydrogen, but I'm not getting any smaller than that, so that's not bad. Hydrogen, not that bad of an escape route. What happens the other direction? For that bottom structure, I have more of an escape route, which means what about its reactivity? We could predict its higher reactivity, which means lower stability, which means higher energy. Which product should be formed? The lower energy product. Okay. So out of this, what we end up with is something, or a nice little rule that can become out of this, and that's our Zaitsev rule. Okay. And there's a bunch of different ways we can look at it. What we just walked through was type B, our kind of hand-wavy, which way is more difficult for a pi bond to react. Doesn't quite work, but it's close enough and gets us the answer. Strictly what we're looking at is a Hammond postulate looking at the transition state for each of those reactions and deciding which one is easier to go through and do. It's a lot of work, but we could potentially go through and do that. So we could look at an energy diagram and look at the energy diagram for A, B, and C. I've got the intermediates on there. Where's the energy for A, B, or C? How would you put them in there? Oh, C might be nice to show up. There's C. B is going to be the lowest energy. Well, there's all the answers. B, C, A. What is that going to mean for the transition state? Our transition state is going to be largely based off of our reactant, which is up here, our intermediate. But we're going to have a secondary effect by lowering the energy of each of those products. Which one's going to occur faster? B, because lower activation energy. Okay? That helps us kind of get through and do that. And what that's coming from is, again, what's known as the Hammond postulate, talking about the energy of your transition states, okay, relative to everything else. Okay. Heat of hydration. It's another fun way to look at this. What is heat of hydration referencing? Heat of hydration is how much heat it takes to react with H2 to make it a saturated alkene. Your heat of hydration is starting at your alkene and taking it down to an alkane. Okay. what is the heat of hydration of B relative to C? B relative to C. Smaller, less heat of hydration. It is lower in energy. Okay. So you can see all sorts of questions come back to heat of hydration. Not a big fan of it. It shows up once or twice. Kind of be aware of it. The energy diagram is the only way I've ever been able to answer a question on heat of hydration. Okay. This was our kind of hand-wavy argument. We're always going to form the most substituted double bond because it's more stable. Why is it more stable? There's more things preventing the double bond from getting out and reacting. Okay? So when we go through to do an elimination, whatever you got to do, make it the most substituted double bond. Okay? So we can go through and look at all of those results. This rule is known as Zaitsev's rule. Why? There was some famous Russian chemist that found this out first. So it's known as Zaitsev rule. So you might hear things referred to as a Zaitsev elimination. What we're saying is the product of that elimination reaction produced the most substituted double bond. Simple as that. Okay. You notice that I also said through this whole process that you should always do this. Always is a relative term. Roughly 90% of the time, most substituted double bond. There is, of course, an exception. That exception is referred to as the Hofmann elimination because guess who discovered it? Hofmann. Okay. And what he noticed was that in an E2 reaction, so it's not one we have to worry about for our E1, but under E2 conditions, if your hydrogen is sterically hindered, we need a sterically hindered hydrogen and a sterically hindered base. Okay. If those two things are true, when we go through and do the elimination, we'll form the least substituted double bond. Fairly rare. It does show up in the homework. I just helped someone with it. I don't remember who it was. You? Which question was it? 8. I think it's back-to-back questions. 8, then 9 in chapter 9. 7 and 8 in chapter 9 activity. That's what you're getting at. So what you need to do is evaluate your base and decide, is that a sterically hindered base? Ooh, you should be leaning towards Hofmann. Okay, is it a sterically hindered hydrogen? Lean towards Hofmann. As long as you got both those conditions met, you should have the Hofmann product, not the Zaitsev product. Okay, so you're choosing between two options. It's a quick little example. Have at it. So we look at our products. Try and color code, because everybody loves color coding. It's showing up, right? Our blue product. And our purple. Those are our 4 possible products. What we did was that's 3. We removed a hydrogen and formed our pi bond. So in the case of the red one, we took the electrons away from that hydrogen and we put them into the pi bond. In the case of the blue one, we took the electrons away and we put them into a pi bond. Purple, into a pi bond. Those are our 3 possible results. Of those 3, which is our favored product? Deciding that, we want to look at how many substituents are on each. So we identify the carbons of our double bond, and we look at the atoms attached to those carbons. Okay. If they are not hydrogen, that counts as a substituent. So if we go through on the red one, there is 1, 2, 3, 4 substituents. If we look at the blue one, there's only 1, 2. If we look at the purple one, 1, 2, 3 substituents. Of those, which is the most substituted? The one with 4. All of these have 4 things attached to the atoms of the double bond. They have to. Otherwise, we don't have proper octet rules satisfied. Okay. But what ends up happening is that we now evaluate what are non-hydrogens, because hydrogen isn't going to do much to stabilize anything. All right? Questions? Tough. Moving on. Okay, E2, I would argue, is probably even harder than the E1 as far as the elimination. We're getting the same kind of concept coming out of our E1. Where our pi bond is forming, we need to have the leaving group leave and the hydrogen be removed in the exact same plane. Just like when we pulled off the hydrogen, it had to be in the same plane as the p orbital. Why? So we get p orbital overlap. If we look at our leaving group leaving, it's starting to form a p orbital. So the electrons that come in to stabilize that must be coming from the hydrogen coming into that p orbital. So we have to have our electrons, our leaving group and our hydrogen, in the exact same plane. So if we take a look at two possible reactions, okay, yes, I did do this right. You'll notice that in both of these E2 reactions, we end up with only one product. What is the difference between these two reactions? So that's the product. And yes, I absolutely agree, there is a difference there. But in those cases, in each of these reactions, virtually identical conditions, we end up with one cis and one trans. Why? What is the difference that's causing one to be cis and one to be trans? It's not a rotation, it is stereochemistry. If you take a look at the carbon of your leaving group, the stereochemistry of that carbon has changed in each of these reactions. That change, nope, that change forces the result. Okay? We will pick it up there because we are definitely well done. I will say, as far